Within our solar system's collection of diverse worlds, each celestial object possesses distinctive characteristics that set it apart from all others. Certain bodies have become permanently suspended in geological stasis. Mars represents a frozen desert landscape, while Pluto remains encased in perpetual ice. Other worlds exist beneath dense atmospheric shrouds, as demonstrated by Venus and Titan. Yet among these varied environments exists an entirely different realm. This world experiences constant internal turmoil from catastrophic geological processes occurring deep within its structure. Numerous molten volcanic systems launch massive eruptions unpredictably toward space. An enormous planetary body dominates the majority of its celestial view, occasionally obscuring the distant, faint solar disk. Expansive valley systems display countless variations of yellow and red coloration across their surfaces. This describes Io, Jupiter's satellite, a world simultaneously hazardous and violent, while remaining magnificent and extraordinary. Scientific investigation of Jupiter's satellite system produces numerous breakthrough discoveries annually, enabling space exploration technologies to integrate increasingly into everyday human activities. Our exploration now takes us toward Jupiter's volatile and unpredictable satellite. Over 400 years ago, during 1610, Galileo Galilei accomplished one of history's most significant astronomical achievements. Using his modest observational instrument, which appears primitive compared to contemporary equipment, he identified 4 distinct objects positioned in Jupiter's vicinity. One received the designation Ganymede, now recognized as our solar system's largest natural satellite. 2 additional bodies, Europa and Callisto, have emerged as promising targets for extraterrestrial life investigations based on current research conclusions. The 4th satellite, located closest to the massive gas planet, received the name Io. Extended periods passed during which technological constraints prevented detailed surface observation of this celestial body, leaving its composition and internal architecture as subjects for theoretical speculation. Nevertheless, through progressive scientific developments, astronomical researchers accumulated increasingly comprehensive information over successive decades. Current understanding establishes that Io ranks among our solar system's largest satellites, exceeded in dimensions only by Ganymede, Titan, and Callisto. Its radius spans 1,135 miles, while its mass totals approximately 8.9 times 10 superscript 2 kilograms. Comparative analysis between this celestial body and Earth's moon reveals nearly identical physical dimensions between these 2 objects. However, mass comparison demonstrates that Io possesses 21% greater mass than our planet's primary natural satellite. This indicates that this cosmic body maintains higher average density than any other satellite within our solar system. Computational analysis establishes density at approximately 3.5 grams per cubic centimeter, significantly exceeding most non-metallic geological materials. Understanding the mechanisms behind Io's exceptional density requires examination of its internal structural composition. Contemporary theoretical models of celestial body formation suggest that Io contains a relatively concentrated central core composed of iron and sulfur elements. This core region encompasses roughly 20% of the satellite's total mass. Radius measurements, according to various scientific estimates, span from 220 to 560 miles. Mathematical calculations demonstrate that these dimensional parameters would generate insufficient internal thermal energy to liquefy the majority of core material. This conclusion receives additional support from the virtually complete absence of any detectable magnetic field emanating from this celestial object. Computational modeling reveals that the satellite's core exists within a surrounding solid mantle structure, composed of at least 75% forsterite, a magnesium-bearing mineral compound. Calculations indicate that the mantle's outermost section exists in molten state, creating a magma ocean approximately 30 miles in depth. Temperature measurements within this region reach approximately 2,900 degrees Fahrenheit, exceeding 2,400 degrees Fahrenheit above standard reference points. Deeper structural layers remain under extreme pressure conditions, maintaining solid states despite experiencing considerable thermal energy levels. The mantle structure receives coverage from a lithospheric layer with thickness measurements ranging between 7.5 and 25 miles. Despite possessing substantial thickness, this layer lacks monolithic integrity. Throughout various surface regions, the celestial body's exterior develops crack formations, generating extensive fracture systems filled with molten lava material. Spectroscopic analysis demonstrates that unlike the majority of natural satellites, Io contains virtually no water, ice formations, or frozen gaseous compounds. The celestial body's external surface consists primarily of basaltic material and sulfur compounds, while also incorporating deposits of various high-density mineral formations. This compositional characteristic explains the satellite's exceptionally elevated density measurements. Prior to the 21st century's beginning, Io's surface had undergone investigation by no fewer than 5 automated orbital research platforms. However, the most essential information emerged during the 1970s decade through the Pioneer and Voyager exploration programs. Within transmitted imagery sent by these probes to Earth, scientific teams identified massive gaseous eruption events, with certain examples achieving altitudes of 310 miles. This observational breakthrough initiated a revolutionary chapter in solar system scientific investigation. Previously, actively erupting volcanic systems were documented exclusively on Earth. For the first time, astronomical researchers observed beyond our home world not merely solidified lava formations or volcanic systems that had ceased activity billions of years previously, but ongoing eruption processes that in various aspects exceeded Earth's volcanic phenomena in impressiveness. Comprehensive analysis identified approximately 400 active volcanic systems across the satellite's surface, roughly 2.5 times fewer than those documented on our planet. However, the satellite's surface area measures significantly smaller than Earth's, establishing Io as our solar system's most volcanically active celestial object. Such an extraordinary celestial body naturally attracted intense scientific scrutiny from astronomical researchers. Throughout successive research missions, investigators accumulated vast collections of photographic documentation across varying resolution specifications. This comprehensive data collection enabled scientists to construct a complete geological mapping of Io during 2012. The resulting cartographic quality permits identification of the satellite's most significant topographical features, including plain formations, mountain range systems, lava flow patterns, and naturally, numerous volcanic structures. Among the most striking characteristics stands an immense orange-brown circular formation positioned within the satellite's southeastern region. This extensive feature spans more than 620 miles and matches the area coverage of major African nations. Scientific interpretation suggests this formation resulted from sulfurous eruption deposit accumulation originating from the ancient Pele volcano, situated at the ring structure's center. Photographic analysis conducted across both infrared and visible spectrum ranges reveals that the ring's central area contains this volcano's patera, a complex multi-tiered depression measuring 19 by 12.5 miles, containing molten lava material. Surface temperature distribution of the molten geological material remains uneven and undergoes constant variation, achieving peak temperatures of 2,400 degrees Fahrenheit at the most thermally active locations. Scientific theory proposes that the patera maintains connection through subterranean channels to the satellite's molten mantle structure. Lava material within the fracture system experiences continuous agitation because volatile chemical compounds dissolved within attempt upward movement, transporting molten rock flows in the process. Consequently, the thin solidified material crust covering the lake's surface experiences periodic cracking and structural failure, generating eruption flashes and lava discharge events. Certain examples can achieve altitudes exceeding 190 miles, propelling solidified gray rock particles directly into space. Under gravitational influence, volcanic debris gradually decelerates, disperses across the satellite's surface, and subsequently settles downward. This process creates the massive ring formation clearly observable from space. Many of Io's volcanic systems produce similar structural formations, though Pelé's ring represents the largest among all documented examples. Active volcanic processes constitute the primary mechanism driving Io's distinctive atmospheric characteristics. Available scientific data indicates that the satellite's gaseous envelope maintains extreme thinness and consists predominantly of sulfur dioxide compounds. Density measurements vary dramatically across different geographical regions. Within volcanic plume areas, for instance, gas pressure measures 25 million times lower than Earth's atmospheric conditions. Simultaneously, during eruption events, atmospheric pressure on the celestial body's sun-facing hemisphere averages 1 billion times less than familiar terrestrial values. The satellite's night-facing hemisphere exists in nearly complete vacuum conditions. Atmospheric density measurements there register 1 trillion times lower than Earth's atmospheric density. Additionally, despite the atmosphere's extreme rarefaction and absence of an indigenous magnetic field, aurora phenomena have been documented on Io. Electrically charged cosmic particles, accelerated within Jupiter's magnetospheric environment, bombard the nearby satellite, producing multicolored atmospheric luminescence. However, contrasting with Earth's aurora patterns, Io's aurora displays most frequently manifest at equatorial latitudes, since particles following demonstration trajectory paths must penetrate the thickest atmospheric layers at those locations. Our continuing exploration across Io's terrain will proceed in a northwesterly direction. After traversing beyond Pelé's sedimentary ring boundaries, we will encounter the expansive Busal mountain range system. This formation's overall diameter measures approximately 335 miles. Among various summit formations, an enormous peak designated South Busal demonstrates particular prominence. Possessing base dimensions of 90 by 99 miles, this mountain elevation extends more than 11 miles above the satellite's mean surface level, twice the altitude of Earth's Mount Everest. The complete elevation system encompasses nearly 7,000 square miles, comparable in size to smaller European nations such as Montenegro or Slovenia. External appearance and structural characteristics of this topographical feature suggest formation through massive tectonic catastrophic events. Presumably, during remote historical periods, a lithospheric fragment tilted and partially descended into the mantle structure, while one edge remained permanently elevated above the surface level. Consequently, the mountain's southeastern slope creates a precipitous cliff formation approximately 9 miles in height, ranking among the solar system's highest escarpment structures. On Earth, such geological formations would be impossible due to elevated gravitational forces, while on other planets and satellites, low tectonic activity prevents such features. Therefore, South Busal can be considered a genuinely unique solar system peak formation. Continuing northwest movement will bring us to an enormous chasm known as Loki Patera. This geological structure represents Io's largest volcanic depression, with diameter measurements reaching approximately 155 miles. The total area of this tremendous collapse formation exceeds 19,000 square miles, roughly 1.5 times the size of Lake Baikal, among our planet's most spectacular freshwater bodies. However, unlike Earth's aquatic systems, this fracture contains not water, but molten sulfur silicate lava material. Deep within the interior structure, several dozen miles below the surface, this lava lake maintains direct connection with the mantle, serving as an inexhaustible source of molten geological material. During quiescent periods, the Patera's surface temperature oscillates between 26 degrees Fahrenheit and 104 degrees Fahrenheit. These relatively moderate values result from upper lava layer cooling as they contact Io's rarefied atmospheric environment. Subsequently, these layers gradually solidify, developing a slowly expanding solid crust whose mass achieves critical thresholds over 4,600-day periods. Following this time frame, the crust fractures under its own weight and submerges, generating flooding waves that traverse the lake's surface at approximately 0.6 miles per day. Eventually, The lava lake stabilizes and again begins developing a slowly solidifying surface layer until the subsequent flooding cycle commences. Due to the nearly complete absence of water and carbon dioxide on Io's surface, essential components for sustaining life as we comprehend it, this celestial body is considered unsuitable for biological genesis processes. However, conditions on Loki-Patera's surface and other lava lake systems could theoretically support the development of unusual life forms capable of withstanding extreme temperatures and deriving energy from chemical reactions involving sulfur or iron compounds. Similar organisms exist on Earth, primarily within underwater volcanic vent systems or isolated oceanic cave environments. Nevertheless, considering Io's tectonic activity and extreme surface temperature variations, the probability of such phenomena remains quite minimal. Meanwhile, observation reveals that although elevation and volcanic features represent Io's most distinctive topographical characteristics, they occupy relatively limited surface area. Tectonically active surface zones are separated by extensive regions of relatively level terrain covered with substantial sulfurous deposit layers. When observed from space, such regions exhibit lighter coloration, with the largest examples extending across thousands of miles. For example, traveling westward from Loki-Patera while passing numerous smaller volcanic systems and lava flow formations, one will encounter a region designated media. This area represents a bright, relatively smooth irregular space surrounded by mountain formations and large patera structures. Its diameter, according to various scientific estimates, measures approximately 1,615 miles, with surface area corresponding to roughly 12.6% of the entire satellite's surface. The majority of this region maintains uniform and smooth characteristics. However, at certain locations, lava flows connected to neighboring volcanic systems intersect the plain formation. Scientific hypothesis suggests that lithospheric layers beneath media possess increased thickness, creating structures analogous to Earth's continental formations, explaining why such extensive surface areas maintain structural integrity over prolonged periods. An alternative hypothesis proposes that the satellite's upper mantle layers exist in fragmentary molten states, with liquid magma absent beneath tectonically inactive plain regions. Observational data demonstrates that unlike volcanic regions, Io's plain areas exhibit frigid climatic conditions. Media's temperature measurements, for instance, do not vary significantly from average values across the entire satellite, measuring only -198 degrees Fahrenheit. This represents hundreds of degrees colder than most volcanic patera systems. Under such temperature conditions, sulfur dioxide from atmospheric emissions deposits as frost across the satellite's surface, creating smooth and gradual terrain colored in hundreds of yellow, red, and black variations. Regardless, future research investigations will certainly provide substantially more comprehensive data regarding this region. After traversing the gentle contours of Media's sulfurous hill formations in a northwest direction, we will encounter another major depression known as a Mirani. Like most other volcanic systems on the satellite, this represents a crustal breach filled with lava material. Its diameter at the broadest measurement reaches only 23 miles, yet when viewed from space, this volcanic system appears nearly as prominent as Io's largest surface features. The explanation lies in a Mirani being surrounded by several massive, solidified lava flows that contrast dramatically with their dark coloration against adjacent bright plain backgrounds. The largest flow extends northward for more than 186 miles, achieving widths of 37 miles. Therefore, this topographical feature constitutes the solar system's largest active lava flow formation. The second largest flow formation extends westward for approximately 155 miles. Previously, this was considered a separate geological formation, but following detailed surface imaging acquisition, it became evident that this feature also represents part of a Mirani. Additionally, a fan pattern of smaller dark flows extends eastward from the primary patera, whose coloration suggests composition of molten and subsequently solidified silicate materials. A Mirani possesses complex internal structural characteristics. Scientific assumption indicates that beyond the primary active zone, additional magma conduit systems exist beneath the satellite's surface throughout this region. Their periodic breakthrough events cause eruption activity beyond the main depression zone. Infrared spectrum observations demonstrate that the primary patera maintains heating to approximately 2,960 degrees Fahrenheit. Temperature measurements of surrounding individual thermal hotspots achieve 2,130 degrees Fahrenheit. Such elevated thermal readings apparently result from an ascending magma flow positioned directly beneath the volcanic system, transporting molten material from deeper mantle layers. Available data also suggests that Amirani most likely represents a very young shield volcano formation. Over time, the lava material it erupts will construct an extensive flat shield structure hundreds of miles in diameter, and quite probably this volcanic system will develop similarities to Mars's Olympus Mons. The fact remains indisputable that relative to its modest size, Io demonstrates extremely anomalous tectonic activity levels. After all, due to its limited mass, it lacks adequate reserves of radioactive materials whose decay processes provide internal thermal energy for most planetary bodies. Scientific consensus attributes this celestial body's non-standard activity to tidal interaction mechanisms with Jupiter. Combined with orbital resonance effects maintaining Io in stable orbital patterns, the gas giant's gravitational influence intensely heats the satellite's interior while simultaneously deforming its crustal structure, creating conditions for frequent and powerful eruption events. When combined with reduced gravitational conditions, these become genuinely spectacular phenomena. Massive eruptions reach space, sustaining dispersed particle cloud formations around the celestial body. Some materials fall back onto Io's surface. Others receive acceleration from Jupiter's magnetic field, bombarding the planet's atmospheric system. Still others settle on the gas giant's additional satellites or contribute to its ring system materials. Precisely such magnificent eruption events occur continuously within a region designated Tvashtar Patera, located within Io's northern section. This region represents an area of pronounced volcanic activity spanning approximately 186 miles in diameter. According to available scientific data, several volcanic patera formations exist within this territory, presumably connected to a unified underground lava source system. Throughout the past 3 decades, multiple powerful and extended eruption events have been documented in this location. During 1999 to 2000, for example, eruption altitudes achieved 239 miles, while volcanic deposits covered surface areas with radii exceeding 435 miles. Additionally, during this eruption event, enormous quantities of sulfur silicate lava material spilled from the patera, inundating vast adjacent areas. Several years subsequently, in 2006, another major eruption commenced in the identical location, persisting for 530 days, thereby establishing the record as the longest catastrophic event throughout Io's entire observational history. During this instance, the eruption column achieved 205-mile altitudes, dispatching thousands of tons of material into space. Clearly, Tvashtar represents an extremely active region from tectonic perspectives. Investigation of its eruption products will enable acquisition of extensive data concerning this satellite's internal composition and structural characteristics. Stating that Io represents a unique and fascinating celestial body whose investigation continues would not constitute exaggeration. Specifically, on February 3, 2024, the Juno orbital platform conducted a flyby at 930 miles altitude above the satellite's surface, transmitting numerous high-resolution photographs to Earth. These images reveal enormous fracture systems within the celestial body's crustal structure, along with volcanic plume formations and lava flow patterns. Expectations suggest that similar flyby operations in future timeframes will facilitate spectroscopic analysis of Io's atmospheric composition to refine understanding of its chemical makeup and physical parameters. Nevertheless, despite astronomical community interest in this celestial object, no dedicated research missions focused on its investigation are currently under development. The JUICE and Europa Clipper projects concentrate on investigating Ganymede, Europa, and Callisto due to their potential biological habitability characteristics. Although NASA specialists announced development of a mission-designated IVO at the century's beginning, intended to focus on Io's volcanic systems, various factors prevented its implementation. However, volcanic phenomena and spectacular eruption events continue fascinating us today with the same intensity as during their initial discovery. The opportunities for observation and investigation remain enormous. Ultimately, every increment of scientific knowledge advances our civilization's progress. If such numerous remarkable mysteries can be uncovered even within our solar system's boundaries, then beyond those limits, throughout the Milky Way's vast expanses, countless astonishing discoveries certainly await us. Until our paths cross again.